Okay, so we're going to go back now and start to take a look at example number 4 here. We're going to look at example number 4. We'll pause and move on to the next video where we'll do example 5. All right, so let's see. Here's what we have. Quote, bystanders perform CPR correctly less than half the time, end quote. At least according to a USA Today article, which noted that among the cases in which bystanders gave CPR, 305 performed the CPR correctly, but 357 did not. I'm interested in testing the article's claim that less than half of CPR bystanders performed the CPR correctly. I want to test that article's claim at a 0.03 level of significance. Okay, completely ignore that last sentence for the moment. We'll talk about that in a second. I'm going to just start right at the beginning. You can see I'm going to kind of outline those 4 basic steps that we had on a problem like this. I'll show you kind of where everything goes and how we can think about this. All right, so right at the beginning, I know that I want hypotheses. I know I'm going to have an H1 kind of versing off versus an H0. And I know that in here, I can see that I'm asking about a percentage of people who are going to be doing CPR correctly. So I want to have P as some value in both of these. And I'm interested in guessing what this value of P might be. But I can kind of see that USA Today is kind of already doing a part of this guess for me. Notice in that quote, they say bystanders perform CPR correctly under half the time. So if P is all of the people that perform CPR correctly, then USA Today is claiming that P is under 0.5. That's the claim right now that's being made. Now, automatically, I can see that this had to be H1 because there was not an equal sign there. But once I know that this number, actually, I'll highlight that number in blue. Once I know that this number's here, it automatically has to go over here. These numbers will always match. So if P is equal to 0.5, I'm going to verse that off with P is smaller than 5. I want to know, is the percentage of people that do CPR correctly under 50% or is it 50%? Which of those would I think is the more reasonable conclusion to reach? Okay, so this seems to be what we're working with. I'll notice that this value here is the value P0, like we had talked about in the previous video. Okay, the next thing that I do is I would go to the test statistic step. And what I'm going to be interested in trying to figure out is what is all the different sample evidence that I have collected. So the article has some things that have been given to us. First, it gave us a value of X. It gave us a number of people that did CPR correctly. That was 305. It also gave us a total number of people that were surveyed. Now, it kind of indirectly gave us this value because it said there were 305 people that did it correctly, but there were also 357 that did not. So if I calculate that, I'm going to get 662 total people. With this, I can go ahead and compute my p hat value. I can see what percentage of these 662 people did CPR correctly. So I'm going to go ahead and set up 305 people out of 662 did this correctly. And now I would have to kind of jump to my calculator. So if I pull my calculator up here, waiting for it to load, and then I'll have to quickly resize. Oh, look at this. Someone was working on box plots. Very exciting. I can go ahead and actually crunch out here my value, 305 divided by 662. And I'm going to get 0.4607. Okay, so right now it seems about 46% of people are doing CPR correctly. All right, I want to know if this is an easy p hat to get, if the real p is 50% and I just got lucky, or I want to know if this is evidence that the real p is actually below 50%. I don't know which one of those is right, so I'm going to go ahead and run some checks. I want to check to see what the distribution of the p hats is. So remember, there are 2 checks that I have to do. I need 20 times n is less than or equal to capital N. So I need 20 times 662. Let's see what that gets me. So 20 times 662 is 13240. And I want to know, is that less than or equal to n? So if n is the total number of bystanders that have ever done CPR, do I think there are more than 13,240 people that have performed CPR. And I don't know the exact number, but I'm going to guess that's a pretty darn safe bet. Okay, check number 2. I need to check that n times p times 1 minus p is greater than or equal to 10. Now I know what my n value is, but notice I don't know the value of p. That's why I'm doing the test. But I'm going to then assume H0 is true until, or H0 is at least innocent until proven guilty. So that means that I'm going to not use the value of p, but like the formula sheet suggests, I'm going to use P0 because that's what I believe P is. That's why on the formula sheet here, you'll see I use P0s instead of Ps. But either, I'm going to go ahead and say, I believe that value is 0.50, and then 1 minus that value of P should still be 0.50. So I'm going to go to my calculator, oops, and I'm going to go and do 662 times 0.5 times 0.5. I'm going to get 165.5, which is greater than or equal to 10, and I can check that off. So I can conclude p hat has a normal distribution. Perfect. The last thing that I can do is I can set up for my Z-score. I don't actually really care if you do it in this step or in the next step. So I'm going to kind of do both of these steps, finishing this second one and the third one kind of at the same time. Okay. In the next step, what I can start to do is the same thing that we've always done. We can say, there are a lot of p hats that are possible. I could put them on a number line. I know they form themselves into a nice normal distribution because I met the checks. I know that the average of the p hats is whatever I believe p is, which is 0.5. And I could get the standard deviation, but for the moment, I'm going to hold off on writing that and finding that like you did in the homework problem and you did in the earlier examples in this section. Instead, what I'm going to go ahead and do is I'm going to place my value of p hat on the number line. We got the value 0.4607, so that's a little below average. 4607. And we would be interested in knowing, is that likely or unlikely to happen if the real percentage is 50%? So I can also kind of set up, again, Z-scores. I haven't found the Z-score yet for my p hat value. I could if I wrote everything out, but I'm going to see that the calculator can give me all of this information really, really quickly. Let me show you how to do that. Okay. All right. I know that if I wanted to do a lot of things in a stats class on the calculator, I can click on the stat button, okay, on the calculator right here. And this is normally where we would edit a list and stuff, but I don't want to do that. I'm going to go over to this tests menu on the side, and there's a whole bunch of different tests. I'm going to look for this option down here, number 5, or it might be close to number 5. It should say one prop Z test. In fact, that's exactly what the formula sheet tells you that you would want to look for on a problem like this. Okay. So I'm going to click on that, and notice it's going to ask me for all the information that I already wrote down. It wants to know what's P0. Well, we already said that's 0.5. That's the number from the hypotheses. What's our value of X? Well, let's see. Sorry about all the screen switching here. Our value of X we said was going to be 305, and our N was 662. This last line down here is asking me what the alternative hypothesis looks like. What is H1? Now, in here, you can kind of imagine that you could cross out what that ROP. It's trying to shorten proportion, but we should have something that looks like our alternative hypothesis here. So this is kind of like filling in the second half of our hypothesis, because we have P. Should that be not equal to 0.5? Should it be P is smaller than 0.5? Or should it be P is bigger than 0.5? Well, in our case, we selected this option. So I'm going to use the over arrow to select, and then I can go down to calculate. Now, once I do this, a whole bunch of information is going to pop up. One of the first things is a confirmation that this is what our alternative hypothesis said, and that is what we had. It also tells me my Z-score. I'm going to go ahead and write that down. It was negative 2.0210. It's no surprise that it's negative because our value is below average. And I can fill that number in on the number line. It also tells me this is the value of p hat that you found, and here's your n. The value that's actually brand new is this value, and I'm color coding it in blue for a reason. That value is blue because it stands for this amount of space in the picture, and it's what we call the p-value. It's a probability value. Essentially, we can state this. That p-value, that amount of space, that is equal to the probability of getting a p hat that's less than 0.4607. Now, normally, if we wanted to compute this, we would do normal CDF, and we would do, like a -1E99 up to the 0.4607. We'd put in the mean, the standard deviation, we'd crunch all of it out, and we'd hit enter. But here's the best part. The calculator already did that. And it already told us the answer is 0.0216. The calculator did the entire normal CDF. I don't have to do it. But now I can immediately start to answer, is this something that's rare or not rare? Could this have happened by random chance if the real value was 50%? Or could it seem unlikely to happen by random chance? Well, what we can see here is that this is rare. Now, typically we would say this is rare because it would be below 5%. But what we see in a hypothesis test is that from time to time we might want to adjust how we determine whether something is rare or not rare. And this is ultimately going to be done by taking a look at the value of alpha. Alpha is our level of significance. That's why in the problem we were told, test the article's claim at a 3% level of significance. So what this is saying is that while normally something that occurs under 5% would be rare, on this question, we're going to assume that stuff under 3% is rare. Of course, this doesn't really change our answer. We would still say that the p hat that we saw is rare. So I would go ahead and I could kind of word all of the following stuff. I can see here that my p-value is less than my alpha. So we have a rare sample. If I see something rare, then it doesn't feel like H1 or H0 is a good fit. So I'm going to choose to reject H0. Now, this is at least just kind of my opening thoughts. It's not really my conclusion yet. My conclusions are always going to come in a two-sentence format. It'll be the same style two sentences every time for the rest of this semester. Here's how it's going to work. The first statement I'm going to use is just to describe the p-value. So I'm going to state this. I'll say it is unlikely to get a sample percent of 46.07 by chance if the real percentage is 50%. That's what we saw. That's sentence one. It describes the picture and the p-value. It was weird to get this value here if 0.50 is what was supposed to be in the middle. It's weird to get this if H0 is correct. My second sentence would always state what it is that I'm concluding. So I would say, we have enough evidence to conclude that, well, technically that H1 is the better hypothesis. But I'm never just going to write H1 is better. I'm going to state, what did H1 actually say? And if I go back up and I look, I can see that H1 said that P, the percentage of people that perform CPR correctly, is under 50%. So I'm going to write that. We have enough evidence to conclude that the percentage of bystanders who perform CPR correctly is under 50%. Done. I have a two sentence conclusion. It's always going to talk about that p-value interpretation and then which hypothesis do I believe. Notice that this should be something that anybody in our class should be able to read and understand. So I don't want to reference like the level of significance. I don't want to reference the hypotheses by name, like H0 or H1. That's not what I want to do. I want this in the context of the problem. Okay. The last thing that I should always again recognize is, at the end of the day here, we've picked hypothesis 1 as the better hypothesis to go with. But could we be wrong? Well, of course. And if we could be wrong, we should ask the question, what type of error could we make? So we'll say here, we picked H1 and could be wrong. So we may have made a type 1 error. It's totally possible. It would be very wrong, though, to replace those underlined words with more strong language, like we picked H1 and definitely were wrong, so we made a type 1 error. Those things we can't say. We don't know if we're right or wrong yet. This is just our educated guess. The only way that we could ever know in statistics whether we're actually completely right or completely wrong is if all of the data came in. If you got every single person in the world who had done CPR and were able to assess whether they did it correctly. But again, that's the whole point of statistics, is that while that sounds like an overwhelming feat, statistics gives us a way to make a very, very educated guess without ever knowing the correct answer. And so if we had to guess off the top of our head or guess based on statistics, this seems like the way to go. Okay, in the next example, we'll take a look at the next example in the next video, and we'll see what happens when we modify this slightly to a two-tailed test. Most of this we'll see is exactly the same.